In the last unit, we talked about work. And at the very end, I told you that work can be converted into kinetic energy. In this unit, we're going to follow up on that and explore the concept of energy a bit more. And I will show you how you can use energy to solve mechanics problems. To go back to the last unit, work was already a form of energy. And work that you do can be calculated as the force times the displacement. So let's quickly recap with two simple examples. The force of gravity, if you need to do work against the gravity, for instance, if you're lifting something, gravity locally is a constant force, mass times gravitational acceleration. So the work that you need to do is simply this force times the displacement. So if you lift a stone for a height of 1 meter, the work you need to do is simply mass m times g times the height of 1 meter. So if the stone is 1 kilogram, you need to expend about 10 joules to do that. For, say, a spring, on the other hand, the force is not constant. Or if you have, say, a rubber band, like I have here, if I want to pull the rubber band into some extension, right now the force is 0, but the further I pull, the larger the force becomes. This is described by Hooke's law, which states that the force is linear in the extension or the compression of the spring or the rubber band. Now, if I want to calculate how much work I need to do to extend this rubber band, I can't just multiply the force with the extension anymore. I need to integrate over the force. Now, this is a linear function. Integrating a linear function is fairly straightforward, and we get a quadratic function. So the work that I need to do to extend this rubber band up to some distance u is a half times the spring constant times the distance u squared. Now, this work, when I've extended this rubber band, the work has not gone away. It's stored in the deformation of the rubber band. The rubber band has gotten what's known as potential energy. And when I relax the rubber band, if I do this slowly, it's exerting a force on my hands and actually doing work on my hands as it goes back to its relaxed state. So this work that I'm putting in now, I'm, as it were, getting back when it's moving back. Of course, I could also let go, and then the work is converted not again, the energy that's stored in the rubber band is converted not again into work, but into kinetic energy. And at the very end, when the rubber band is colliding with my hand, the kinetic energy is converted very quickly back into work, done with the force on my hand, and then converted into heat. And so a little bit of deformation and into heat. So potential energy is the work stored in a system, work that you can extract from a system. And work that is stored in potential energy can then be converted either into kinetic energy or into deformations. And for the spring, right now, so here I'm slowly getting the work back. Here I'm converting the work into kinetic energy. Now, when does something get converted into motion and when does it get converted into heat? That depends on the forces that are acting on your system. And in general, there are two kinds, conservative and non-conservative ones. For a conservative force, all the work done is stored as potential energy. Examples are the gravitational force and the spring force. If I've lifted something up, all the work I've put in against gravity has been stored into potential energy of that object. The same thing is true for the rubber band I was just stretching. All the work I did on stretching it was converted into potential energy of the rubber band. And I can get it back out by going in the opposite direction. For non-conservative forces, the work done is lost to dissipation and is converted into either deformations or more generally into heat. And examples of these are the friction force and the drag force. There is no potential energy for friction because work done against friction is lost, at least from the mechanics point of view. There's a pretty easy way of seeing whether a force is conservative or non-conservative. And this is by asking yourself the question, can this force accelerate an object? All forces can decelerate an object. So if you have, say, a frictional force because an object is sliding over a surface, the object will always lose speed. Friction can never cause the object to accelerate. Whereas spring force or the gravitational force can cause objects to accelerate. If I would drop my remote, gravitational force is certainly going to accelerate it downwards. So forces that have the capability of accelerating things are typically conservative, whereas the forces that are not capable of doing this are non-conservative. So if you have a conservative force, you can thus convert your work into potential energy and potential energy into kinetic energy. As long as you're not exerting external forces on the system, you have something known as the total energy of the system, and that will then be conserved. So in the example just now, when I was stretching the rubber band, I'm adding work into the system because I'm actively pulling on it, so I'm exerting a force. But once I let go, there's no more external forces acting on the system, and the only thing that can happen is that potential energy is converted into kinetic energy, or kinetic energy could be converted into potential energy. But the total energy of the system will then be conserved. We can show this in equations, but we can also show it graphically. So here we have a sketch of the potential energy as a function of position. This particular example, it has some maxima and minima. For spring force or the rubber band, it would have just a single minimum because this is a quadratic function. This has the shape of a parabola. There may be a couple of springs pulling on something, and so we have multiple minima. The total energy in this landscape, or in this plot, will always be a horizontal line. Unless you're acting on it from the outside, the total energy has to be conserved, and so the total energy is the same everywhere. And now finding the kinetic energy is very easy. It's simply the difference between the potential energy and the total energy. So once we know the potential energy and we have the value of the total energy, there's no more need to actually graph the kinetic energy because it's exactly the same as the potential energy, just mirrored upside down. This thing is often referred to as a potential energy landscape because it tells you the potential energy as a function of position in space. So it could actually be a real landscape. But that's more of a technical term. You can also just see it as a graph here. So what can we do with this? Well, so for conservative forces, so for forces for which we have a potential energy, this is an extremely powerful tool of solving mechanics problems. And it's much easier than doing it with forces, because forces are vectors. You always have to think about directions. Whereas energies, total, kinetic, potential, and also work, are just numbers, which you can add and subtract. Therefore, let's do two examples. Let's revisit local gravity, where the force was a constant. And therefore, the potential energy is simply, well, it's the integral over the force, but it's simply the force times the displacement. So the potential energy for gravity, which undoubtedly you've seen before, is mass times gravitational acceleration times the height. And so if I, say, drop a stone from some height h, well, I can use Newton's second law to calculate what happens. But I can also say, well, I know the potential energy at that height h was mass times gravitational acceleration times h, and that can only be converted into kinetic energy. Kinetic energy is a half times the mass times the velocity squared. So if I want to know how fast this thing is going, once it has fallen this height h, well, all I have to do is equate the original potential energy to the kinetic energy. And now I can rewrite this thing and immediately find that the speed that this object will have is given by this expression. You might notice that here the mass is taken out, right? The mass appears both in the potential and in the kinetic energy, which means that if you drop two objects from the same height, also if they don't have the same mass, they will still get the same speed once they have reached the ground. Now this is a fairly standard example that you have likely seen before. Let's make it a little bit more interesting. Let's go to larger scale gravity. There's also gravitational forces between the Earth and the Moon, or between the Earth and the Sun, and those no longer obey this simple law. There's a more general version of the gravitational law, also from Newton, which states that the gravity between two massive objects is given as the product of their masses divided by their distance squared times some universal constant, which is known as the gravitational constant. It just has some fixed value. Now, if here we can use to study larger scale motion. For instance, you do rocket science. So the first thing we do is we say, well, we need to figure out what the potential energy of this thing is. Now here the gravitational force is no longer constant, right? It depends on the distance between the two objects, and actually the square of that distance. So we need to integrate this. We have to be a little bit careful. Before, when we integrated the constant gravitational force, we integrated from 0, ground level, to some level h. Now, if we want to integrate this gravitational force, the more extended version, if we put in 0 for the distance, this thing is actually going to blow up. So that's not a very good reference point. You would have an infinite force and also an infinite potential energy. However, here if I take my reference point at infinity, then the gravitational force is going to go to 0. So instead of integrating from 0 to some distance, we're going to integrate from some distance up to infinity. Now that's an integral over 1 over r squared. Now the r, again, like we had before with time, where we integrated over time and time was a limit, I'm going to replace the r in the integral with rho, the Greek letter. So I'm integrating of 1 over rho squared. That becomes 1 over r. And then I substitute the limits, right? Infinity, which gives me 0, and r, which gives me the product of the masses divided by the distance between the masses. So this is now the potential energy of an object an object that's subject to this gravitational force. So this goes for the Earth as it goes around the sun. It also goes for a rocket that you're shooting up. And one of the things that you can very easily now calculate is how fast I should shoot up the rocket such that it can actually escape Earth. A rocket is just like a stone that's being thrown up. The main difference is that the rocket goes much faster. And if I want to know how fast it has to go for it to be able to escape Earth, well, it needs to overcome the potential energy difference between infinitely far away and on the ground. And on the ground is not r is 0. On the ground is r is the radius of the Earth, because it's the distance between the center of the Earth and the rocket. And that potential energy should be the same as the kinetic energy that we give the rocket when we fire it. So again, we simply equate potential energy and kinetic energy. So in the potential energy, we're now going to substitute the mass of the Earth and the mass of the rocket, and dividing by the radius of the Earth, and we equate that to the kinetic energy, which is still a half times the mass times the velocity squared. Again, the mass of the rocket doesn't matter, it drops out, and the escape velocity is given by this square root. And you see, things that come up here are this universal gravitational acceleration, the mass of the Earth, and the radius of the Earth. Now the mass of the Earth is pretty large, so escaping from Earth is pretty hard. And in order to be able to do that, you need a pretty big rocket. The Moon, on the other hand, is somewhat smaller, but especially much lighter. So escaping from the Moon does not require such a big rocket, which is why back in the 1960s, when they went to the Moon, they had this huge Saturn V rocket, which was over 100 meters tall. Whereas when they came back from the Moon, they could make do with this tiny rocket, which was maybe 1 meter tall. So I've hopefully shown you how you can use energy to solve mechanics problems. We'll of course have some examples and exercises with that. And in the last unit, we're going to look at what happens due to this force of gravity and other forces when things are moving in circles around each other.